Everyone, so we are going to do our Pset1 solutions. So let's go ahead and get started. So titanium can exist in BCC or HCP structures. BCC is typically more brittle, HCP is more ductile. BCC will often, fracture more easily in terms of strain. I can change the structure via heat treatment procedure called annealing, where I place titanium in a furnace for a certain amount of time temperature, and I'm trying to make a very ductile form of titanium. So I heat treat the material to convert from BCC to HCP. And I can ensure the structural change by characterizing the sample with techniques like XRD or an SEM, should be SEM, scanning electron microscopy, with an EBSD detector. Describe my process and identify each corner of the material's tetrahedron. So I'm going to draw a horrible tetrahedron, like so. So we know in our materials tetrahedrons, we've got structure, we've got properties, we've got processing, and now I've got my credential, but I'm not going to do that. Processing, and then we have over here performance. And then in the middle, right at the center, that's us. So we are doing the characterization and all that other good stuff. Characterization, modeling, experiments, all us. So, what's happening here? Well, we said that we are going to do a process called annealing, where we're going to put the material in a furnace for certain high temperatures for long times, and that is going to reduce. I'm going to have material before I anneal it that has lots of dislocations, a high dislocation density. Dislocation density could be 10 to the 14th dislocations per meter squared, and I could, by doing this process, I could change the structure and reduce the dislocation density to about 10 to the 7th, per meter squared. So I'm doing a process called annealing to change the structure of my material, not only reducing the dislocation density, but also I'm going from, in this particular example, hypothetical example, from BCC to HCP, making it even more ductile. So I've done a process, annealing, to change the structure, and that is going to change my properties and performance. By doing this process, I am going to effectively be, and I'm going to scroll down here, I am going to be changing my properties, like my yield strength is going to decrease, my ductility, strain at failure, is going to increase, and other properties will definitely remain the same. So the performance in an application will change. And again, we're at the center. What are we doing? We're doing XRD, we're doing SEM, we're doing EBSD detection. So that is essentially the entire process here. So kind of a little nice one, but just a reminder of kind of the cool materials tetrahedron that we work with essentially in this course. So that's it. First problem done. So let's erase here. And let's read the next one. Correct the following statements that are false. If everything is correct, simply state that they are true. Conditions for Bragg diffraction are constructive interference. True, we need constructive interference, but what else do we need? Well, we need basically, we need constructive interference, we need some wavelength, we need obstacles that are spaced, a periodic array of obstacles, so that's another thing that we need. And the distance between these obstacles, we need to make sure our wavelength is on the order of that distance. So we need constructive interference, that's when we see something, but again, for Bragg diffraction, we need these kind of additional components to do. Some wavelength, some periodic array of obstacles, and we need that wavelength to be on the order of the distance between those obstacles. So we see a peak in intensity when destructive interference occurs? No, constructive. I can measure the distance between atoms on the order of angstroms with the green laser. No, green laser, about 400 nanometers. My wavelength there, we're trying to think, that is 400 nanometers, this is an angstrom. No. Finally, Bragg utilized simple geometric relationship to recognize that diffraction can occur if waves constructively interfere, and thus the x-ray from travel must be equal to half an integer wavelength multiplied by the wavelength of the incident beam. No. So remember, the key thing that we saw in our derivation, and in Bragg's derivation, a plus b equals c plus d is equal to an integer times the wavelength. So to have constructive interference, we need to be in phase, and it needs to be an integer number there. So again, a little kind of a tweak and a little kind of true or false, but kind of getting into what's happening here. What bonding is occurring? Or excuse me, not what bonding is occurring. That's the next problem. Kind of how do we describe Bragg diffraction? It is a difficult concept, so don't let that kind of fool you. So yes. All right. So next problem. For the following elements, materials, list the types of intramolecular actions. Inter, describe how electrons are distributed. For molecular interactions, which these interactions spontaneous basically formed. What are the relative energies of each interaction? So again, intra, we know that those are covalent, those are ionic, and those are metallic. So if I do that, and I know this is on the order of 200 kT, ionic is about 80 kT, this could be metallic is around 20 kT, but they're all over 8 kT. Inter, those are things like van der Waals, H-bonds, steric interactions, dipole-dipole, etc., 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 and those are all less than kT. So these can be broken and reformed at room temperature, these cannot. We also know delocalization in metallic bonding, localization, this is sharing the electrons, this is taking away the electrons. The van der Waals interactions, those are kind of like these kind of quantum, basically these kind of quantum fluctuations in your electron cloud field. So what interaction is going to occur here? SN, that's a middle, it's tin, it's going to be metallic bonding. PVC, polyvinyl chloride. So let's go ahead and let's actually draw out the structure of PVC. So it actually looks a little bit similar to our polyethylene that we've kind of written before in class. So let's go ahead and let's write down PVC. PVC is essentially that white pipe. If you've ever kind of worked with, pipe essentially. So PVC is going to look like this. So H, C, and then just a tiny change from our old friend polyethylene. Actually, here, let me I'm going to undo. Actually, I'm just going to use my eraser. I should have just changed it to typing. Alright, so there it is. So, what interactions are going to occur here? Well, we've got covalent bonds along the backbone, but then again, we'll have these kind of van der Waals actions with these chlorine. You might have some dipole-dipole interactions because it's very electronegative. And actually, just by changing this chlorine to an H, we get polyethylene. But PVC is much essentially stiffer than polyethylene. And actually, it has a much higher TG than polyethylene, just due to that change, that chlorine group. So very, very interesting, to me at least. So anyways, lithium chloride and chromium dioxide. How are we going to figure those types of bonding out? Those aren't metals. They're clearly not just covalent. They don't have any intramolecular interactions. Well, let's go ahead and we're actually going to go ahead and upload this live. This is exciting. Figure out the table. I'm going to insert a file printout, and I'm going to look at some downloads. Periodic table right here. And let's go ahead and let's see. Uh-oh. Secured. Things are happening. I know this is just fascinating to all of you, but please be patient because it's all worth it, because it'll be nice once we actually get to work with this. If this does indeed work. Uh-oh. Let's hold out hope. Don't worry. Just take it nice and simple. Let's see what we got. There we go. All right. So we were working previously with lithium chloride. So LiCl and chromium dioxide. So I need to look at what's my electronegativity difference. So let's go ahead and find it, or figure out how do we find our electronegativity. So we're going to go ahead and look. I shouldn't have drawn it there, but you can see electronegativity is right here. It's the second one, this 1.91. So right above from the electronic structure. So if I go to lithium, I see that my electronegativity is 0.98 and chlorine is 3.16. How do I know that? I have no life, and I've memorized that. So chlorine is 3.16. Very important chemistry. So I think it was 0.98. Now I'll remember lithium. So let's go down, down, down. Now I've messed it up again, and you're probably getting dizzy. I know that Zoom and online learning can be 0.98. So 3.16 minus 0.98. I'm going to use Mathematica because I can't do math anymore. And I want to double check and not look foolish on this YouTube video. So let's open up our Mathematica document. So 3.16 minus 0.98. And what do we got? 2.18. So that is, in fact, an interaction that is ionic. because it's greater than 1.7, like we saw in our notes. What about chromium dioxide? So let's look at oxygen. Actually, we'll look at chromium. So chromium is 1.66. So let's go ahead. 1.66. I'm going to do minus because I know that oxygen is more electronegative, but let's go ahead and let's check that out. Oxygen is 3.44. So let's see if we hit the magic number. 1.44. Is that 1.7? Yep. So they're both ionic interactions. So both of those are going to be ionic. So that's how you figure out basically how you figure out the interactions. Excellent. In a BCl2 crystal, identify the cation and the anion and the valency of each, which will gain electrons, lose electrons, so BaCl2. Again, I can look it up, but I know that chlorine needs 1 electron to complete its electronic structure, so Ba is going to give up. Ba is the cation, is 2+, Cl is -1, and I know that I need 2 of these in order to grab those. So you can kind of confirm that on the periodic table as well. So let's go ahead and we can be a little bit, just kind of a chemistry reminder. So Ba is on the second row. So again, these are going to be, want to give up 2 electrons. So Ba is the cation, Cl is the anion. So those are the valencies. And then what about CSF? So CS +1, -1, same principle. U is going to be 4+, O is going to be 2-. And again, I need 2 of those. So again, this number here denotes the amount. So I need 2 oxygens. So I'm going to have electronegativity. I must maintain electroneutrality. So that's the key kind of concept here. All right. So the next question is asking us about our Leonard-Jones potential. So I'm going to hop over actually to our to another book. So let's go ahead. Let's visit our graduate friend. Let's go into some potentials. So we have quite a bit of potentials that we can work with here. So this is the Leonard-Jones potential. So I'm going to go ahead and type that right now. So the Leonard-Jones potential, my LJ, so ULJ equals 4 times epsilon, and then I'm going to do sigma divided by r to the 12th minus sigma divided by r to the 6. All right, so let's go ahead and go back to our problem. So that is our Leonard-Jones potential. Where is here? There we go. Now, my researchers, my undergraduate researchers, they're at it again. I always make fun of my undergrads, but they are actually amazing researchers. So it tells me that I'm trying to approximate the binding potential for iron using an LJ potential. So I find that my epsilon equals 0.83. My sigma equals, again, these are fitting parameters, 1.545 angstroms. I'm going to convert that to meters right now because I want to work in meters. EV, I need to make sure that I kind of know that that is an electron volts. That's an energy. We could convert that to joules, but at this point we don't need to use it. So did my undergrads correctly approximate the equilibrium distance between Fe atoms? So what is the potential? So I need to find the equilibrium distance. So I know my equilibrium distance is when my energy is minimized. So I'm going to take the derivative of ULJ with respect to R, take the derivative, and I'm going to solve for when this is equal to 0. It should solve automatically. So I get lots of potential R's, but I'm going to do the one that's not negative and not imaginary. So this is my equilibrium distance. So do distance equals this. So 1 point, oops, for some reason it's not copying. Here we go. So this is my equilibrium distance in meters. So the question is that my equilibrium distance? So I know in iron, my nearest neighbor distance is 2r, the metallic radius. So iron, let's go ahead and look, again, looking at this handy periodic table, we could also look at the metallic radius. So the metallic radius is the second one down here. So let's go ahead and look at iron. And we can see that iron, Fe, is 1.26 angstroms. So my equilibrium distance would be 2r. So 1.26 times 2 would be 2.52 angstroms. So not quite. So something's a little bit off. so far. But let's keep answering the question. So now, so this is not right. So we'll get to why it isn't in just a second. So what is the energy? What's the potential energy at this equilibrium distance in joules? So I'm going to plug in that ULJ slash dot R goes to, I'm plugging in R for my equilibrium distance, and that's negative 0.83. That is electron volts. I need to convert electron volts to joules. So I'm going to do, when I don't know, I'm just going to go electron volts to joules conversion. So 1 electron volt is 1.602 times 10 to the minus 19. So 1 point times 0.602 times 10 minus 19. And voila. So that is my energy in joules at that equilibrium distance. That's the lowest energy state. Fantastic. According to this potential, at what distance is the force maximized? So I know the force, my force is equal to the negative gradient of ULJ with respect to R. Now you find when force is maximized. So I need to take the derivative of force with respect to R, and I need to solve again. I need to solve, set this equal to 0, and here we go. So this is the distance where my force is maximized. Fantastic. So should they publish the results using this potential? So the answer in terms of why doesn't our answer match? My undergraduate didn't mess up. We shouldn't be using the Leonard-Jones potential to approximate metallic interactions. So that's the big problem. Is we can't use those to solve these types of problems. We need to use a better potential, metallic potential. So they should not publish the results. What distances will the atoms repel? So at distances less. So when I look at my Leonard-Jones potential, let me look over here. I'm going to right here. So we found our equilibrium distance. So if I look at my Leonard-Jones potential, so here we are going to attract. Here we're going to repel. So distances larger than our equilibrium distance here. Larger distances they will attract, closer distances they will repel. And then we've just illustrated that. Fantastic. All right, let's go to the next question. LDPE, so low density polyethylene has lots of these kind of like side branches here. It's different from HDPE, which has very few side branches. We'll kind of talk about that in just a second. But anyways, LDPE has these branch states. So, and there's different, the branch states can basically be in different isomeric states, specifically stereoisomeric states. So just like we saw in class, atactic, isotactic, or syndiotactic. So isotactic, being, for example, on the same side, or syndiotactic being some repeating feature, and then atactic being just completely random. So you get the picture. So we know that for polymers, their properties will very, very, very rapid, or they depend on how close, or essentially how well these intermolecular actions, how well the intermolecular actions can get closer, because we know that some of those interactions decay, especially Federal interactions, d to the minus 6. So we know that the force, as they get larger and larger and larger apart, they get weaker, 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 weaker. So we need to stack these polymers efficiently. But if I have branches, there's only so many ways I could kind of pack them. So if there's a branch sticking up, I can't put a polymer in this same location. Two atoms can't occupy the same space. So if I want to basically create a polymer with the highest melting temperature, or with the stiffest properties, which arrangement is going to be best? Well, it's going to be my isotactic first, because I could pack these guys and extend it here. I could extend it here. I could then put the next one here. Syndiotactic would be next, because again, I know where some of those side chains are, but the atactic is the most unpredictable. I'm going to have to put lots of space to make sure I don't, overlap there. So that's essentially, that's a great answer, or a good question. Not to toot my own horn. Finally, look at those two pairs. Are they isomers, conformers? Neither, both. So I can't rotate around this double bond. So these are isomers. Specifically, isomers. They are geometric And they are cis and trans. Cis here, trans here. What about over here? Are these conformers or isomers? It's an isomer, so I can't rotate, those kind of independently here. So if I rotate around, this angle, I can't rotate around kind of two bonds here. But again, this is a little bit of a tricky question. I could kind of forgive you if you, said these are isomers. But technically, again, I can't rotate and twist without having, each of these kind of being separate. But anyways, the key thing here is we see that they're both chemically identical, but they are still, again, they're chemically identical. And here, in fact, that they're actually structurally distinct. You can't kind of do a twist around there without kind of putting those separately. But anyways, excellent. So that is Pset number 1. I hope it's been insightful. Use this to study and then do well on Pset 2. I think people do really, really well on this problem set. So thanks, and I'll see you in the next video. Bye. Have a great day.